Hello and welcome. Today's focus is going to be on Lewis diagrams. Now we've been talking about bonding, both ionic and molecular, or covalent, and today our focus is going to be visualizing it, being able to see how the bonding works, being able to draw and show that ourselves. So the first key concept to discuss, and hopefully this will be review, but is the stable octet. This idea that all elements want to have a full valence shell. So that outer shell of electrons, we want it to have a full 8 electrons. And we'll talk about later on, we're going to discuss the middle, sort of the transition metals a bit more. There's some changes to that rule. But generally 8 is that full shell. Certainly with the first 20 elements that we're going to talk about, that 8 is ideal. So that's what we'll be working with mostly. And again, we want a full 8 electrons in the outer shell. So atoms will tend to shed, share, steal, move electrons around to get this stable octet and become ions. Now it's much easier for metals here on the left hand side, even over here, to the sort of 1, 2, 3, those first 3 columns, to lose electrons. Right? You want a full 8, it's much easier to lose 3 than to gain 5. These guys over here on the right hand side, sort of columns 15, 16, and 17, they certainly prefer to gain electrons because it's easier to gain 3, gain 2, or gain 1 than to lose 5, 6, or 7. So these tend to lose electrons. In the case of molecular compounds now, or covalent compounds, you're going to see sharing of electrons. And again, we've discussed why that happens. Now we're going to see it, and hopefully this will help you visualize how that happens. In terms of there's some exceptions to this octet rule. Certainly hydrogen and helium, if you look, there's only 2 elements in this first row, and that signifies the fact that actually a full octet for these 2 elements is actually only 2. So it's not an octet, since only 2 fill it. So hydrogen only needs to either gain 1 electron or lose 1, and helium has 2 electrons, it's full and happy. Another exception is beryllium and boron. Beryllium with 2 electrons, boron with 3. Okay, in their valence shell are electron deficient, so they tend to have 5 or 6 electrons in the valence shell when they are satisfied all of their bonding needs. So sometimes they're not quite that full 8. Sometimes they'll have 5 or 6 to be happy, which is a little bit interesting. And then periods 3+, they have these d orbitals that can be filled. And so again, when we start talking about the transition metals, there's a bit of an exception to that rule. But again, we'll discuss that later. For now, let's talk about the first 20 elements or so and having a full octet. So the first step is to be able to draw Lewis diagrams for simple atoms. And in any case, or all of these, we're just going to start by drawing electron dot diagrams for the individual atoms. So an example of NaCl, okay, this is an ionic compound, right? A metal and a non-metal bonded together, and we're going to draw the Lewis structure for that. So the first step, sodium, we'll draw the Lewis structure for sodium. Symbol is Na. We see that it's in the first column, and so it has 1 valence electron. Chlorine, with a symbol of Cl, has 7 valence electrons. As we can see here, it's in that 7th column. So we know 3, 4, 5, 6, 7th column, 7 valence electrons. So we can see very obviously now sodium wants to give up an electron, chlorine wants to gain an electron, and so sodium's electron just leaves and joins chlorine. Now it's no longer an atom, it's become an ion. Sodium has lost an electron, chlorine has gained, so we're going to draw square brackets around each of these now ions, and we're going to put the new charge that's occurred up there. So sodium is now +1 since it's lost an electron, chlorine is now 1- since it's lost an electron. So this is a Lewis structure for the ionic compound of sodium chloride. Aluminum oxide underneath, again a metal and a non-metal, is a trickier one But we're going to start again the same way. So we're going to draw the Lewis structure for each of these compounds. Aluminum is in the third column, so it'll have 3 valence electrons. Oxygen is in the 6th column, so it has 6 valence electrons. Okay, so now if we were to draw all this out, you'll notice that if aluminum were to try to give all of its electrons to this one oxygen, it won't work. As we can see here, there's still one left over. So we need a second oxygen atom. So this electron now comes here. Unfortunately, now this oxygen is not full, so we need a second aluminum. And then again, unfortunately, this aluminum has leftover electrons, and so these two need to come to this oxygen. Now this is messy, right? And so to simplify this whole process, we know from here that there are 2 aluminums in this compound. So we're just going to draw aluminum, again the Lewis structure for aluminum, with a 2 in front of it. Now oxygen, we know there are going to be 3 from there, so we're going to put a 3 in front of the Lewis structure for oxygen. And now in each of these cases, we're going to draw the ion. So aluminum loses its electrons. It lost 3 electrons, so it becomes 3+. Oxygen gains 2 electrons, so it becomes 2-. And now we have the proper sort of demonstration of this compound. 2 aluminums at a 3+ charge and 3 oxygens at a 2- charge. Okay, now in terms of ionic compound, molecular compounds, there's this we're going to approach this in a similar way to begin, and then things will change, because now we're dealing with elements that are sharing electrons rather than giving and taking. So we'll start by putting the first element, or the one with the least number present, in the middle. So we're going to draw the Lewis structure for carbon first. Carbon is in the 4th column, so it has 4 valence electrons. Now I can see that I have 4 chlorines, so I'm going to put chlorine, 4 chlorines around the outside. We're going to spread them out evenly in all these cases. And then I'm going to put my 7, because it's in the 7th column, valence electrons around chlorine. Now, the tricky thing here now is when electrons are being shared, a bond is created. And when this bond forms, the electrons that are connected by this bond count for both elements. So the 7 chlorine electrons are still there, but this now bonded one from carbon counts. And now I have 1, 2, 3, 4, 5, 6, 7, 8 counted as part of chlorine. And I still have 3 here with 2 extra to give me 5. So I need to connect all of these bonds. And now each of these elements is happy, right? I have 1, 2, 3, 4, 5, 6, 7, 8 around the carbon, and again 8 around each of the chlorines, showing that I have my full valence shell in each case. So this is what your final diagram should look like. Whoops. Sorry, with the carbon in the middle. Okay, let's do it one more time here with silicon dioxide, right? Because there are 2 oxygens and 1 silicon. So again, 1 silicon, it goes in the middle. Silicon has 4 valence electrons. So I'm going to put 4 valence electrons right around the outside. I have 2 oxygens. And oxygen is in the 6th column, so it has 6 valence electrons. Okay, now we can see oxygen wants 2, right? There's 2 empty ones. Silicon needs 4. So what we can do to fix this problem is to draw double bonds. So if I draw a bond here, again this oxygen has 1, 2, 3, 4, 5, 6, 7, but another bond here gives us 1, 2, 3, 4, 5, 6, 7, 8 around oxygen, just 6 around silicon, but I have this other oxygen handy. Okay, and I end up with 8 around oxygen and now 8 around silicon with these double bonds. So you can use double bonds, and you're always connecting electrons. You should be able to get a full octet for any of the elements that are part of these compounds by creating these bonds, connecting the electrons, and having the electrons count for both. Okay, so just to review, ionic compound between a metal and a non-metal, basically you create each ion, show the full octet in the negative ion, the empty octet for the positive ion, and present the square brackets with a charge on it. Similarly, or differently I guess, with a covalent compound, you're now connecting them and showing shared electrons, but you're still hoping to get a full octet in each case. At this point, hopefully you've taken good notes, and now you can answer the question under the video on Verso.